Okay, so welcome all, and welcome to our sixth and final fusion tutorial. The topic of this tutorial is alternative fusion technologies, and here we're going to be building on the previous five and looking to broaden our scope a bit and look beyond what we do at just UKAEA, other things going on around the globe. So my name is James Roberts. I'm a graduate mechanical engineer, and I'm going to be guiding you through the topics today. The four kind of questions we're looking to answer are: what other tokamaks are out there? What is inertial confinement fusion, which is a term you might have heard? What are the other non-tokamak approaches to fusion? And a little weird one at the end, what is Muon catalyzed fusion? So let's dive right into it. Fusion research at UKAEA fits into a global network of magnetic confinement fusion research. So we are by no means the only ones. We talk about MAST a lot, our spherical tokamak, but there's actually been 38 spherical tokamaks, including decommissioned ones, throughout history. Even more, if you look at conventional tokamaks shaped like jet, there's been 185. So this map here shows a bunch of different operating tokamaks around the world. And a lot of our research is actually done in collaboration with these labs. Many of them are government-funded labs, some of them university labs as well. And I like to say that fusion reactors are a bit like theme parks, in that all of them have got something that breaks some kind of record. So JET, our largest reactor, is the largest in the world and is the most powerful, the only one that can operate with tritium fuel at the moment. But there are many other records out there. So JT60 claims a lot of others, including the highest triple product. So that's the best conditions for fusion. The longest high confinement plasma has gone back and forth between K-Star in South Korea and EAST in China, both of which are superconducting tokamaks as well. So that's something we just don't have on JET. We have conventional copper magnets, whereas these are using superconducting magnets, so can just run for much longer. Of course, on this list of 185, a lot of those are smaller ones. So who are the main players? Which are the main ones we're interested in? Broadly speaking, the major players are the 7 members of ITER. So ITER, being built in the south of France at the moment, will be the largest tokamak ever built, around 10 times the size of JET. And its 7 members are China, the EU, India, Japan, South Korea, Russia, and the USA. So 35 countries total, representing about half the world's population, and I think over 80% of its GDP. And each of these countries operates their own tokamaks as well. And we need results from all of these to build together our cumulative understanding to go into ITER. We just simply can't do the full range of experiments required to get all the knowledge in order to run ITER just by using JET and MAST. So they are a very big part of the puzzle. This is part of ITER being installed a few weeks ago. Remember I said how big it was? This is the cryostat base, which is the bottom of the container, basically, that all of the magnets will sit inside, and as such the vessel sits inside. That is a 1,250 ton part being lowered in. It is absolutely huge. Here is a picture of it from underneath, and these are people there to give you a sense of the scale. So it's absolutely important that we get things right for ITER. You can't be building something this big on a gamble, so it's absolutely essential that we have a range of different results from a range of different tokamaks around the world. But when we talk about magnetic confinement research, we're not just limited to tokamaks. Stellarators are another thing that's being researched as well. This is the Wendelstein 7X in Germany. And as you'll recall from Fusion Tutorial 2, if you've seen that, stellarators are a different way of confining the plasma, still using magnets, but in a different shape, using this coiled ribbon shape, which can potentially offer better stability, so better steady state operating conditions. This is something which has been invested in parallel by UKAEA Fusion. So they're funding both work that goes towards ITER with conventional tokamaks and Wendelstein 7X, looking at stellarators as a kind of potential further development once tokamaks have been built into power plants, or potentially an alternative. So here's a picture of Wendelstein built at the moment. It has run plasmas, it's not just a diagram. And it's another promising technology, but it's slightly less mature than tokamaks are. This is something I'll say a few times throughout the talk. And technology maturity is just an assessment of how close a technology is to being put into production. It's not an assessment of the quality of the technology or whether it beats one or the other. So tokamaks have been researched more and for longer. So that's why they're closer to building commercial fusion power plants. But why do we need so many? I've sort of said we need a lot, but what's the basis? Different approaches in different reactors can lead to breakthroughs in different areas, to put it simply. Here we've got JT60SA from Japan on the left, and K-Star from South Korea on the right, two of those record-holding tokamaks I mentioned earlier. And they can do different things from what we can do in JET. We can try out one diverter configuration, they can try out another. A very obvious one is TCV in Switzerland, is the configurable tokamak, so it can literally change the shape of its plasmas. We simply can't do that on JET, and neither can most other people on their reactors. It's quite a unique one. Also, from an engineering standpoint, more tokamak builds means you've got a stronger supply chain. More suppliers understand what fusion conditions are, what's needed to go into a fusion reactor. It's not just a case of every time we need one, we have to go out and find people that have never done it before. And also as well, that offers more opportunities for UK suppliers to bid for work on other tokamaks that are being built. So up next, the next question we were looking to answer is, what is inertial confinement fusion? Inertial confinement is an entirely different method of achieving fusion, which uses lasers and a target. So it's trying to achieve the exact same reaction, that same fusion of deuterium and tritium of hydrogen isotopes to cause that release of energy, but the method by which they get there is entirely different. So a huge amount of laser power is focused on a tiny pellet of fuel. Now, these pictures are from the National Ignition Facility in the US. There are a number of ICF, for short, facilities around the world, but the National Ignition Facility is by far the biggest one. And you can see here one of the laser halls, and this is their target chamber. So the pellet sits inside that target chamber. And what does that pellet of fuel actually look like? Well, the pellet of fuel sits inside this golden cylinder here, which is quite exciting. And it contains deuterium and tritium, the same fuels we use, and it's frozen in a sphere with the gases inside. And the lasers must arrive symmetrically. If they don't, there can be big instability problems inside the resulting fusion plasma. And you can see how tiny the fuel is here, being held in this implement, much, much smaller than the size of the vessel it's going in. So how does this process actually create fusion conditions? Well, it's all about achieving extreme temperatures, and in this case, pressures. If you remember, we actually use a very low pressure plasma in our tokamaks, but we run it for a very long time. Here, it's very short time, so they go to really, really high pressures. So first of all, lasers arrive at the target. They start heating the surface of the target. Could also be X-rays as well, instead of lasers. And it heats up very, very fast. Then the heated parts of the fuel start to blow off of the pellet in sort of like a rocket stream. And that compresses the pellet inside that's not being blown off. That continues, and during the final part of the compression, the core of the fuel pellet can actually reach a density of 20 times that of lead and reaches our fusion type temperatures, so 100 million degrees C, a temperature that we're reasonably familiar with, but that's a massive density. That huge density, coupled with the temperature, ignites and causes fusion to trigger. And then the fusion burn spreads back out through the whole plasma releasing energy, well, the whole fuel pellet releasing energy as it goes. So that sounds like an excellent process. Where are our ICF power plants then? Well, at the moment, the process is limited by a few factors. Certainly for the current designs, the efficiency of the lasers is a big one. Remember, of course, on a power plant, it's all about electricity in to electricity out. The electricity you put into lasers, you get much less power out of them. So at the moment, the numbers don't quite line up. To give you a sense of the scale, this is an actual fusion burn occurring in a fuel pellet. And this is the size of the laser hall that's powering it. There's 48 huge lasers there to power that tiny targeted fuel. Now, let's say they're not actually that far off. And in future, improvements in laser efficiency, in laser refresh time, could lead to viable power plant designs. Another challenge as well is that it's not a continuous process. You fire one pellet, it goes bang, and you have to load in another pellet and then repeat the whole process again. By no means is that a challenge which can't be worked around, and that's another difficulty on top. And as well as that, they face a lot of the same challenges that we do around neutrons, fuel breeding, and remote handling. So ICF power stations could absolutely be possible, but there's a few technological improvements that need to get there. Better lasers, potentially microwaves, and similar to what I said with the Stellarators before, it's a less mature technology. So they have a longer stretch than magnetically confined fusion does to get to a commercial power plant design. So these have all been very long-running experiments at sort of big government-run research facilities. Are there any other alternatives that we could be looking at, sort of newer, more promising things? There are a variety of other approaches, and before I get into them, I'm just going to go back over, if you recall, the fusion triple product that was talked about in some of the previous tutorials. And it's called the triple product because you multiply together temperature of your plasma, the time that a particle spends in the plasma, so how long the plasma runs for, and the density. And if you times all those together, you get the triple product. Now, what we do is we have high temperature, very hot plasmas, high time, since they're running for a long period of time, but actually very low density. There's only a few grams of fuel in our very big reactors at once. That's not the only way that you can make that number up to be big. Some of the other designs we'll talk about push the density up and go for a lower time to get similar fusion triple products. So the first kind of newer technology I'll talk about is high temperature superconductors. We talked about superconductors in Fusion Tutorial 4, and they're absolutely essential to having a fusion power plant. So it means that your magnets are subcooled to really low temperatures, and you'll notice here this graph is in Kelvin. So this is absolute zero, or minus 273 degrees C. And this up here is about minus 130. And these special compounds, when they're cooled down to those low temperatures, have no resistance. So you can have big magnets running for a really long time without heating up and using very little electricity, which is fantastic for a power plant. So this first set of materials here are the kind of early superconducting materials. You see there, some of them are just straightforward metals like mercury and lead, and more recent ones like niobium tin, still fairly straightforward metal alloys, and those have to be cooled down to really low temperatures, almost minus 270. So you absolutely need to use liquid helium as a coolant to get down that low. And that's what that blue line is. And that's what we're using for ITER. So that's a reasonably established technology now. But since the 80s, there's been more research on what's called high temperature superconductors. So while still super cold, these conductors can run up to these higher temperatures here. So only around minus 130 almost for those most recent ones. Now, what you'll notice straight away is that these are definitely more complicated. These are compounds involving lots more different elements. But, and you might ask yourself, what's the point of doing that? The difference between minus 150 and minus 200 is cold or cold. Well, a key difference comes around minus 190 degrees, which is where you can use liquid nitrogen as a coolant. Now, liquid helium is super light, and all the helium you put in a balloon eventually leaks out, goes off into the atmosphere, and flies off into portion of it will fly off into space. It's a non-renewable resource, and there's only becoming less of. So it's very expensive to get hold of. Whereas nitrogen, 70% of the air we breathe. So liquid nitrogen is about cheaper than a pint of milk, I think Chris said in his talk. So if you can run, in the long term, there might be no option other than to run on liquid nitrogen. And for those, you will need high temperature superconductors. So that's an absolutely very powerful enabling technology looking forwards. So let's forget tokamaks entirely. What other ways are there of pushing up that triple product? Well, one entirely different approach is magnetized target fusion, and it uses hydraulic pistons to physically compress their plasma. So if you think we're compressing, going for a higher density, and that means it probably for a lower confinement time. So each of these pistons around the edge here, we've got the plasma sat in the middle, and each of the pistons compress, that pushes up the density, and that triggers the fusion to start happening. So a little bit more like the inertial confinement fusion in sort of its ignition process, but still working with a large, hot, magnetically confined plasma. So kind of a little bit of an in-between. Saying about the plasma, the way that we confine it in a torus is not the only way of doing it. A field reverse configuration is a different way to confine your plasma. Now, that sounds fairly complicated, and it is, to be perfectly honest. It's not something I understand exceptionally well. I'm a mechanical engineer, not a plasma physicist. But the way I think of it is that it's like basically blowing a very hot smoke ring. So this blue ring shape here is our plasma, and it's blown into shape, and it's sort of self-stable, rotating in position like that. The shape of the magnetic field is not worth worrying about too much, but an important distinction is that there's no center column going through the middle here. So you don't have to have that large center column like you do on jet, or that very small one like we do on Mars, and that can allow you to configure things differently. The benefit of a field reverse configuration from a physics perspective is you can get much higher densities in the core of that plasma ring. So good for the triple product, as we recall. And those higher densities could mean that it's better for harder to use fuels. So we've talked a lot about deuterium and tritium, and all the previous examples have been using the same fuel that we do. But what other fuels are out there? If you could take advantage of technologies like this, what else could you do? Well, one potential other fuel cycle is a proton-boron reaction. This potentially could produce a lone neutron reactor. You'll notice from the sort of equation here, you're putting proton and boron in on the left. Boron, a slightly heavier element than we're used to with our other fuels. And this spits out 3 helium nuclei. You'll notice there's no neutron. That thing we talked about in great detail, and we've gone on in Fusion Tutorial 4 to talk about the problems that it causes. If you don't have a neutron, all of your resulting products just stay inside the plasma. You don't have so many issues about shielding. You don't have so many issues about remote handling. Now, further on in the cycle, some neutrons will be given out, so it won't be 0, but it'll be much, much less than our DT fuels. So potentially you can build a much simpler reactor overall, much cheaper, much smaller. The downside, or the drawback, is the optimal temperatures, which you might have noticed from this diagram. So DT, we tend to run around 200 million degrees, which is pretty hot, I think we can agree, but fairly achievable with a fusion setup. Proton-boron likes to be closer to 1 billion degrees, so 1,000 million, potentially even higher. So that requires a very, very, very high heating requirement. So not impossible by any means, but that's a big technological hurdle to come over. I've talked about a range of different approaches here. So to kind of preempt the question in your minds of, which do I think is best? Well, different approaches can have entirely different applications. If I compare to aerospace, my aerospace degree betraying itself a little bit here. If you think about the jet engine, it is the same core technology, and when used in different ways, can come up with entirely different applications. It's not to say any one of these is better or any others worse. They just have different pros and cons, so they find different uses. Now, the same could be said potentially for future fusion technologies. And this variety of approaches is benefiting us in the short term too, because exactly as we said with magnetic confined research at the beginning, different approaches can lead to different solutions. It's this variety very positive for the field. It leads to a very healthy research environment and a very healthy engineering environment, the same benefits of the suppliers extending to the other technologies as well. And overall, can be seen as a very good thing and exactly the kind of thing we want to encourage in UKAEA. Now, I will say that tokamaks are still the most proven. They're the most mature of these technologies. And that's why we are continuing to pursue them. It's something we have a lot of expertise in as well. But these different benefits and drawbacks, we sort of wish an absolute success to these other technologies. And these are the things we want to encourage. We want the fastest route to fusion possible. Another benefit as well of some of these different approaches is it has seen a large increase in private investment in fusion. So on top of the government investment, there's been around $1 billion of private investment over the past 5 years. So overall creates a very healthy picture of fusion research going forwards. So at the end here, I promised to answer you a question about what's Muon catalyzed fusion. It's pretty weird. Let's get into it. So Muon catalyzed fusion, it's a physically possible reaction and it's never going to produce net power out. Preface that at the beginning. So it's another way of convincing the nuclei to fuse. Everything else we've talked about so far is about getting them hot, getting it dense, getting it in there for a long time. This is completely different. So to talk about what muon catalyzed fusion is, I'll have to explain what a muon is first. So we remind ourselves of the electron. Now, an electron is a fundamental particle, very small, negatively charged, part of an atom. A muon is a similar particle in that it's also got a negative charge, so it can do the same jobs that an electron does. But a key difference, and you can think of it kind of like an exotic electron, is that it decays very quickly, whereas electrons live forever, and it's much, much heavier. Its mass is 207 times heavier, in fact. So it's a very, very heavy electron that will disappear very fast. If you had a collection of them, 2.2 microseconds later, half of them are gone, another 2.2 microseconds, half are gone again. So they disappear very, very quickly. But how on earth is a heavy electron going to get us any closer to fusion? So muon catalyzed fusion, if we think about a hydrogen atom, which is what we've got here on the left, we've got two nuclei and they're bonded by 2 electrons. Now you can artificially replace these electrons with a muon. And if you do that, recall that the muons are 207 times heavier. That cinches the whole particle up and reduces its radius massively, way more than my PowerPoint animation suggests. It will reduce the radius by a factor of 200. So suddenly now these two atoms in this molecule together are much, much, much closer together. And in their random vibrations, they are much more likely to collide. This means that fusion can now happen at room temperatures, even all the way down to cryogenic temperatures, which is actually where some of the experiments have been done at, down close to absolute zero. And these experiments have been done back in the 50s. So that's great. Let's go out, get some muons, build a muon catalyzed power plant. And as I say here, this makes it so much more likely that it's going to happen. The issue comes with getting hold of the muons. They do occur naturally. They happen in the upper atmosphere when solar radiation bombards it, and but they decay incredibly quickly, and they're sort of gone by the time they've arrived. So it's possible to make them artificially, but it requires a particle accelerator to create, just like the ISIS accelerator over at Harwell, which is another scientific research campus based near ours at Culham. So it's a very large particle accelerator, and they produce muons as well as neutrons. So this is one of their target stations, and you can see here they've got these beamlines which they create muons on. The difficulty here is that for each muon, it costs about 5 gigaelectron volts to create. Don't worry about the units too much, but just remember this number 5. Now, when the muon goes on to catalyze fusion reactions, the most energy you can get out on average is going to be 2.7 gigaelectron volts. Now, it's apparent straight away. You put in 5, you got out 2.7, that's still a negative number. There's just no way of making that come out positive. So yes, muons are useful for science. ICES actually use them for imaging. They send a beam of muons through objects and they can look through them without damaging them. But unfortunately, that reaction is never going to prove useful for creating power out. Now, whilst we're talking about fusion happening at conditions that are not hot, it's worth paying mention to cold fusion. So cold fusion is a term usually used to describe an experiment by Professors Fleischmann and Pons in 1989. And this here is our experimental setup. The results at the time indicated that fusion had been achieved in a room temperature test tube. Now, a lot of serious scientific work was undertaken to try and corroborate these results, and the evidence suggested that no net energy out was being shown. So possibly a case of misinterpreted results. But despite this, the ideas received a large amount of media attention, disproportionate amount, and that's kind of understandable because the promise of fusion, as we've gone to great lengths to explain, is absolutely massive. And if there's a shortcut out there, then that idea really excites people. So let's summarize what we've learned over the course of this presentation. Fusion research at UKAEA fits into a global network of magnetic confinement fusion research, and a lot of that at the moment is based around ITER. Inertial confinement fusion is an entirely different method of achieving fusion using lasers and a target. There are a range of other non-tokamak approaches to fusion, which could all be possible. And muon catalyzed fusion is a physically possible reaction that's never going to produce net power out. So we've recovered a huge amount of ground over these 6 tutorials. Each of them have hopefully stood up on their own okay, but I would seriously recommend that you check out the others if there are any you've missed. And we hope we've given a good overview of fusion from a technical perspective. Gone over a huge number of challenges and opportunities, and hopefully shown why fusion is an exciting thing for us to be researching, and hopefully given you the tools to ask more questions when you're researching this yourselves in the future. Thank you very much for watching.